Good morning or good day to whoever's watching this. My name is Ope Oluwa, and this is Let's Talk About Compiler Construction. There are other parts to this course, of course. There's the lexical analysis, there's also the semantic analysis, and code generation and code optimization. But for the meat of this course, we will be really focusing on syntax analysis because it happens to be one of the most bulky and the most interesting part of the course. So let's just deal with the basics for now because upon moving to later stages, I mean, we would have to deal with things like parsing and everything. And if we actually have no clue what the bases are, we will probably not understand what's going on in the parsing techniques, basic parsing techniques, operator precedence, and the likes. So because of that, I want to make a video that is just dealing with the basics, understanding what's going on here and there. And I hope that it will be a benefit to you as you watch. So, syntax analysis. In the pipeline, lexical analysis deals with the um, breaking of the streams of the source program into tokens. And then this part comes in the syntax analysis, arranging those tokens such that they actually have a relationship, an hierarchy, basically. So we are creating trees here. And what's the closest things that come to mind when you think about parse trees? They need to be CFG, context-free grammar. And that's the basis of the syntax analysis. For the lexical analysis, we are dealing with regular expressions because we don't really need complex stuff to deal with understanding what tokens are. But for syntax analysis, we definitely need something more complex, and that is why we are using grammar CFG. Now, I would skip a lot of introductory stuff. What's a grammar? A grammar is a precise, easy to understand syntactic specification of a programming language. Um, Yada yada yada. I will draw the structure of um, the the role of the syntax analyzer. Okay, pardon my box, it looks weird. Uh, so let's call this guy Lex, not Superman's Lex. Lexical analyzer. Coming in is the source program. Then the token comes out from the Lex guy, and then we have a parser. Parser. And what goes back is get next token. So what's happening is it's not a info dump. It's not an info dump. It's not that the tokens just all arrive at the parser at the same time and then they just get miraculously attached together and they become a parse tree. No, 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 no. The parser, the lexical analyzer is going to be like a subroutine or a coroutine that is constantly being called by the parser, which is why we have the get token function doing something there. And what does it output? It outputs a parse tree, which then goes on to the rest of the front end, and then we should have an intermediate code representation by the time we are done with this guy. Let me just do this IR. Now, while all that is happening, we still have some sort of connection to the symbol table over here. Symbol table. The lexical analyzer, this guy, needs to know what's going on. Okay, so is this an identifier? Is this a keyword? Attributes and all those stuff. It has to know what they are. Then, after doing all this magic, it sends it into the parser, and the parser also will be like, oh yeah, I got the identifier. What's next? Then it asks for get next token, and then the process continues until the entire source program is, you know, passed. Okay, moving on. Yes, we have different types of parsing methods. We have the universal parsing methods. Sorry, not US. Universal parsing methods like Cook, Younger, Kasami, or Early's algorithm. algorithm. So these guys can pass any grammar. However, they are too inefficient to be used in production compilers. So I mean, if you are trying to compile ancient ancient Egypt language or something, just kidding though. It's just not wise to try and do something that is so universal for production. If you are trying to sell stuff, you don't use diamonds to sell stuff for $50. You get the picture. So it's just inefficient. Now, syntax error analyzing handling actually, because syntax analyzer would not just pass, they will actually have to check if something is working, and if it's not working, they will have to handle errors. So there are different ways of handling errors. I would not spend too long on this. uh, there's the panic mode, there's the phrase level, there's the error production, and then there's global correction. Each of these have different things that they do. Panic mode is not that the computer the parser just goes crazy and it's like, help me. No, that's not what's happening. The panic mode is just basically saying as soon as it spots the error, it starts running towards the end of that line, or trying to escape that, and then it will just keep skipping stuff until it arrives at a designated set of synchronizing tokens, which could be a delimiter, a semicolon, something that we just like say, okay, this line is over. Okay, you are safe now. So that panic mode is just like it just begins racing to escape or something. The next one is the phrase level recovery. On discovering an error, the parser would just like make corrections and try and continue. So let's say you wanted to say x is equal to if x is equal to y, and then you say f x is equal to y. Yeah, it's just going to make that correction and move on like that. But yeah, it might have some drawbacks. The drawback of that is that if the actual error has occurred before it actually found out it was an error, it's going to be hard for it to fix it. So each of these have strengths and weaknesses. Error production has its own, which is just like augmenting the grammar such that, oh, we know what's an error, and then we just add it to it. So once someone makes that error, it knows that that's an error. Okay, so CFGs, we know what CFGs are by now because we've seen automata, but in case you did not know, a CFG consists of a terminal. So let's just say we have A derives alpha. This guy is a non-terminal. This guy could mean a bunch of stuff. So it could be a terminal, a non-terminal. Yeah. So in this case, what do we have? The definition for this, we have terminals. What are terminals? Terminals are the basic symbols from which strings are formed. These guys are like the atoms, atoms of CFGs. They cannot be broken any further. So we have the terminals. The non-terminals, however, are like variables. They can mean something else. They denote set of strings. Um, we also have the start symbol, which is a non-terminal that it's like defines the language. It denotes the language generated by the grammar. And then we have the productions, which are like a set of rules to specify how these things combine, how these guys over here combine to do something. Let's say, for instance, now we have statement derives if expression, statement, else, statement. We'll get to the conventions, and I think it's better we handle the conventions here so that we will not have to face them in the examination hall, which I do not want to meet somebody I do not recognize in the exam hall. I don't know about you. Okay, so defining all those, let's just move on. We would really need to identify what are terminals, what are non-terminals. So let's just take an example. Example. I would have asked if I'm going too fast, but you can reduce the speed or something. So we have expressions derives expression, expression, uh, what am I doing? Expression plus term. We have expression derives expression minus term. We have expression derives. Yeah, by the way, this means derives is like saying that when a transformation happens, it's not an equal to sign. No. Like I gave birth to so. I yeah, I didn't give birth to anybody, but this gave birth to this. This derives that. So forget I said anything. Expression term derives term times factor. Term derives term divided by factor. Term derives factor. Factor derives expression in parentheses. Factor derives ID. Okay, so the questions now that we have is, what in the world are the terminals here? Note that every single thing here shouldn't be overlooked. So what do we have? We have expression derives expression plus term. Question: can plus be a variable that can be broken down into other things like plus mini, plus pro max, plus minor? No. So this guy is a terminal. Expression minus term. Can I make minus have children, like minus baby, minus grown up, minus star, minus raised to power 1 million? No, we can't do that. So minus is also a terminal. Star multiplication in this case is also a terminal. The division is also a terminal. Do not ignore the parentheses. The opening parentheses and closing parentheses are important. These are also terminals. And then ID. We'll get to the conventions shortly, but at least we know that the plus, the minus, the star, the division, the open and close, and ID are all terminals. So what are the non-terminals here? Starting with the expression, we can see that expression is giving birth to denoting. Please do not say giving back to your lecturers. That's just weird. Expression denotes expression plus term. This guy just became something else. Expression became something else again. Expression became something else again. So I mean, if that's not a non-terminal, I don't know what is. So expression is a non-terminal. Yeah, we know that. Term. Term here denotes term multiplied by factor. Term also denotes term divided by factor. Term also denotes factor. Yeah, that's it. That's a non-terminal. Term factor also denotes the parenthesized expression. Also denotes ID, which is a terminal. Yeah, it's having many children, so please do not quote me when I say that. We have factors. Okay, so the non-terminals are expression, term, and factor. The terminals are plus, minus, star, divided by open, close parenthesis, ID. So that checks out. Moving on to the conventions, which I believe should be the meat of this video. Conventions. Anybody ever been to conventions before? Yeah, that's not what we're talking about. Okay, to avoid having to state what is a terminal, what is a non-terminal, because yeah, we used expression like we just said XPR. What happens when we have E, or we start using U, V, W? Sorry, let's just That was reverse. You get the picture. Y, Z, we go to omega, all these kinds. We kind of need to specify without having to repeat it every time. Oh, this guy is a non-terminal. This guy is a terminal. Yeah, so yeah, you should know by now. I mean, I've been using Z all the time. You should know by now that this is a non-terminal. That's not how we work here. We have to create some form of convention so we do not uh, have to waste our time having to say what is what over and over and over again. So here are the following conventions that we use in, you know, CFG related stuff. Number one, the symbols are used to represent, these symbols are used to represent terminals. Number one, we have lowercase letters at the beginning of the alphabet. Lowercase letters at the beginning of the alphabet. Let me just put that in the parentheses. A, B, C, the beginning of the alphabet. These are without a doubt terminals. If you use A, B, C, and you are talking, I mean the small lowercase versions of A, B, C, and you use them for non-terminals, bro, you are going to confuse every single person that opens your script. So yeah, do not make that mistake. Lowercase letters at the beginning of the alphabet are terminals. Moving on, we have operator symbols, operators. So yeah, you know by now that you cannot break plus into something smaller. So plus is a plus is a terminal. So plus, we have star, we have minus, we have division, all these blah blah blah. These guys are without a doubt non-terminals. You do not need more commentary on that. Punctuations. Punctuations are also terminals. I do not know what semicolon can be apart from a terminal. So yes, we have that. We have parentheses. We have comma. We have full stop. All of these guys are all terminals. I shouldn't expect you to call it something else. Okay. Another terminal is the digits. Digits are terminals. I do not expect 0 to have a baby. I don't expect 1 to have a baby. I don't expect all the way to 9, because after a while 0 to 9 gives back to all derives, sorry, all of the uh, numbers that you could want except for infinity, which we just use this guy, and it's probably a terminal also. Moving on, when we use boldface strings, because in some cases we have if, we have then, we have else, we have while, and those are keywords, and keywords are they are terminals. We can't break them down any further. So let's say yeah, boldface face strings. So if you see anything in bold, don't think wow this is colorful and be like, oh yeah, that's a non-terminal. Boldface strings are terminals. For instance, we use them on keywords, and we also use them on things like identifiers. You see, I'm trying to make it as boldface as I can, and it's not working. Oh yeah, so if, while, okay. So yeah, boldface strings are terminals. Okay, so again we have stuff to represent non-terminals. So here we are talking about non-terminal. Pardon my writing, I write like a child. Number one for non-terminals, let's just call it A. Uppercase letters early in the alphabet. I mean, uppercase letters early in the alphabet. So A capital, B capital, C capital. If you call these terminals, you are going to get 0 in your exams. Why? Because it's kind of ridiculous. We shouldn't use small letters to represent non-terminals. All right. So the letter S, we usually reserve the letter S in most cases for the start symbol. Yeah, without a doubt, S start. I mean, it doesn't get any better than that. You get the point. C, we use lowercase italicized, sorry, italicized names for non-terminals. You see, we use boldface for terminals, boldface. So when you see them looking all bright and colorful and thick like a man's biceps, a bodybuilder's biceps, thick like that, not thick like anything else, thick like that, you should know that is a bold. It's a terminal. Yeah, so these are terminals. So when you see them in lowercase, looking all feminine, italicized, sorry, italicized forms, they are the non-terminals. So in this case, we have stuff like expression. I'm trying to make mine look italicized, but it's not working. Statement. You see, these guys are not in boldface. Yeah, so um these are non-terminals. I think there's still one more. D. Now, because we have cases where we are discussing programming elements like uh, expressions, terms, factors, instead of us writing them in full, expression, terms, factors, we can represent them with capital versions of themselves. Like, let's say, instead of just saying expressions and this and everything, we can just say the big E, the big T, and then the big F. Yeah. So expression, the long form, is just capital E, capital T, capital F. So we are making some kind of exception because earlier we stated that we were using A, B, C, but these are just more like variable stating. But these guys over here, they are programming terms, and we kind of get lazy as computer science people, and we do not like to repeat ourselves too often, and we don't like to write too much words. So expressions, instead of me saying that all over and over again, I just make that E. Saves me a lot of stress. So yeah, that's one half of it. I will just probably end this here as the conventions, but let's just do a few more. I think there should be okay, I'll just brush through and make it quick. Um, Number three, we can have uppercase letters. Uppercase letters towards the end of the alphabet, X, Y, Z. When you are finding big guys like this that are usually the last of the alphabet showing up, they do not just mean, they don't mean, oh, this is a non-terminal automatically. These guys are not exactly non-terminals. I'll tell you what they are. They are grammar symbols. Grammar symbols. So what are the grammar symbols? Grammar symbols can be non-terminal or terminal. This becomes very important down the line because when we start talking about things like LR passers, LL passers, when we are checking through passing tables, you see stuff like X, comma A. Now, because they use X, it should give you some kind of insight that it just means that it's not necessarily a non-terminal. It could be a terminal also. Yeah, because you find something like X is equal to A is equal to dollar sign, the end marker. And yeah, let's not go ahead of ourselves. But you just see that this suddenly sets a completely different tone to things. We all we knew was ABC meant these are non-terminals. These are non-terminals straight up out of the blue. But then we are seeing big XYZ saying I am a terminal or not. That's weird, but yeah, you have to keep that in mind. Know that when you see big uppercase letters at the end of the alphabet, WXYZ, know that these guys are grammar symbols. Grammar symbols could be non-terminals or terminals. So keep that in mind. Number four, when we have lowercase letters towards the end of the alphabets like U, V, W, X. This doesn't say it's a non-terminal. Yeah, yeah. Oh, I'm making these guys too big. These do not say they are non-terminals. No, that's not what these guys say. They say they are possibly empty, strings of terminals. Keyword to note: possibly empty and string and terminals. So when you see small u, small v, small w, small x, those guys are the later part of the alphabet. These guys could be empty and they could be one or more terminals. So we can have a in one of these guys. We can also have empty in one of these guys. So these guys could mean it's empty and could mean a string, not necessarily one terminal. So when you see UVWX in lowercase, it could be a trap. And these things are very important in parsers because some people wonder why we use symbols for something. It's because they are conventions. You do not want to forget these conventions. You do not want to forget them. That's why I'm making them into a video so you can watch it again and again. Oh boy, this is getting long. Okay, now when we start talking about the Greek symbols, lowercase Greek symbols, lowercase Greek symbols. Okay, so when we start seeing this alpha, beta, and gamma, what do they mean? You know, earlier we talked about these guys being a they could mean a grammar symbol, which is either a non-terminal or a terminal. That's what these guys over here are talking about. X, Y, Z, the big version of them. So when do we use these guys over here? When we are asking for possibly empty strings of grammar symbols. Another set of keywords to note for the Greek symbols in lowercase is number one, possibly empty. So it could be an empty string, and it's now possibly empty is the first keyword. Now, string again, you see that it's not restricted to one. This guy over here is saying either a non-terminal or a terminal. One. These guys over here are saying possibly empty, so it can be zero or more of grammar symbols, which means you should be expecting stuff like a b b, blah blah blah, like that. That's what you should be expecting in the lowercase Greek symbols because there is possibly empty string of grammar symbols. Do you understand? I would have loved to ask if you could ask any questions, but yeah, you'll probably be talking to your screen. They'll think you're crazy. You're not. It's normal. Talk to your screen a lot. It helps. Moving on. Almost at the end. Almost at the end. Almost at the end of the conventions. Please do well to know the conventions. They are very important. I would recommend, even after I take tutorials physically, you want to know the conventions. It will help you. To help you make sense of what's going on in your slides. Okay, so on number 6. Whew, a set of productions A with a common head A, call them A productions, may be written as A derives alpha 1, A derives alpha 2, alpha 2. Oh, yes. Yes. Bacchus Noah form. I remember that guy. Let's go. So we have A derives alpha 1, A derives alpha 2. You remember what I said about these guys being a possibly empty string of grammar symbols. So we do not know whether it's non-terminals or terminals that are there. We don't know if it's empty or we don't know if there's a million non-terminals or a million terminals in that place. So moving on, we have A derives alpha 3. All of these guys are all A productions. A productions. So we know that A derives each of these guys. Instead of us going through all the stress and filling this thing, uh filling the entire page with one single line of derivations or productions. Look at that. That's a huge waste of space, and I like saving space. You should try it sometimes. I will just say for this set of A productions, A derives A. Alternatively, alpha 1 derives alpha 2, derives alpha 3, derives blah 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 to alpha n, where n is some infinitely large number we do not care about. So this is it. Look at that. This is in automata we call this Bacchus-Noah form, but here we just say they are alternatives. Yeah. My bad writing. Alternatives of A, or for A rather, for A. Yes. Whew. Now, moving on. Unless stated otherwise, unless stated otherwise, bless me, the head of the first production is the start symbol. Let me explain that. Before we get to like long list of stuffs, like let's say E derives. I need to clear up space. Mm. Let's say E derives T times F C divided by F. E derives FT prime. T prime derives F or empty, blah blah blah. Look at this guy over here. We except stated otherwise, you would just assume this guy is the start symbol. Of course, we said that usually we use S as the start symbol, but in this case we have an E here, and there's nothing we can do about that, right? But it's the head, so because it's the head, we have to use it as the start symbol. So the beginning of the first production, the head of that is probably the start symbol, unless stated otherwise. With that, I will come to the end of this video. Hope that helped you, but thank you for watching, and I'll see you guys in the next video.